so today we will discuss this example. So let me read the question again. Okay. In an air standard dual cycle, so we are looking at a dual cycle here, whereby it's a combination of Otto cycle and diesel cycle. 2/3 of the total heat addition QH occurs at constant volume, and the final 1/3 occurs at constant pressure. So you can see that I know that in the diagram as well. So QH is the total Q in into the cycle. Then we know that 2/3 of it occurs at constant volume, while 1/3 occurs at constant pressure. So the total QH here is given as 2,400 kJ per kg. The pressure and the temperature at the beginning of the compression process, which means state 1, are given as 100 kilopascal and 30 degrees Celsius. Compression ratio is 10. So calculate the maximum pressure, temperature, and the thermal efficiency of this cycle. So you need to calculate P3, T4, and then the thermal efficiency. Okay, so like I said, for this question, the question doesn't really say whether this is a constant variable question or constant specific heat question or variable specific heat question. So in most cases, in this kind of case, you can just use whichever method you want. For us, we will use constant. So technically speaking, when you have this is kind of saying that it is a constant specific heat question, because the gamma, so gamma here is actually K. Sometimes different books will use different, different subject will use different variable. So gamma here is actually K. So they do give you one fixed K value. So in that sense, it is kind of hinting you that it is a constant specific heat question because the K doesn't change. K is dependent on Cp and Cv. But yeah, but exam it will be a bit more clear lah, because here is very dependent on this diagram alone itself. Okay, so of course there are more information that are not given. Let's say how we can solve this first. So again, we need to solve P3, T4, and thermal efficiency. So like I said, we will use constant specific heat method. Okay, so by the question, we know that P1 is 100 kilopascal, T1 is 30 degrees Celsius, compression ratio is 10, and then the total Q in is 2,400 kilojoule per kg. So you don't necessarily have to do it this way, or this is just how this example is solving, because it does list out things that you want to find out. So we know that thermal efficiency equation is this, so this is what we need to find in the end. Then we know that Q minus W equals delta U for closed system. Then we know that for each of these states, the change of energy is just the change in internal energy. But of course, except for one part, which is here, but later we will see. So from here, it also note down that at this point, so here this is a Q out process, 5 to 1. So the Q out process is just the change in delta U. Again, this part is not too important. Like I said, you don't necessarily have to write down like what you need in the final, but if it is easier for you to understand, then of course that's up to you lah. But usually cycle we have a very fixed like steps in this sense. Okay, so for state 1 to 2. State 1 to 2, we know that this is a compression process, an isentropic compression process. So we don't have T2 and P2, so we need to find out T2 and P2 in order for us to proceed to P3, T3, and then T4. So for this question, like I said, it doesn't really state very clearly. So we assume Cp equals to 1.005 and K equals to 1.4. Again, this is actually the same value that you will get if you refer to table A2. Okay, so if you refer to table A2 at 300 Kelvin, you will get these two values. Now, so again, for this particular chapter, if we say use constant specific heat, you can just assume that it is at 300 Kelvin unless otherwise specified. Okay, so T1 to T2 is isentropic compression. So as you have learned, when you're dealing with isentropic process and constant specific heat, and you guess, then you can use the isentropic relation. So again, gamma here is K, okay? So T2 over T1 equals to V1 over V2, gamma minus 1. You can also replace P over there. We have a few versions of this. So then pressure also same thing. So based on this, by using the compression ratio, you can get T2 as well as P2. Okay, so again, for those of you who are not clear, this is the relation that we are using. Okay, so this is the isentropic relation that we say. It is for ideal gas, isentropic process, constant specific heat. Alright, so based on this, you can obtain P2 and T2. Then from there, you can move on. Okay, right? We can move on from P2 and T2, then proceed to looking for P3 and T3. So I think so far shouldn't be any problem, right? Like if you have tried this out, I assume T2, P2 you will have no problem finding, because it's the same method as what I've shown for this. Okay, then I'll move on to the next slide. Okay, so now that we are done with state 2, then we can move on to state 3. Okay, so state 2 to 3 is constant volume heat addition process. So during this process, we have unknown T3 and P3, and now we can no longer use the same relationship because this process is no longer an isentropic process. But we do have one additional information for this process, which is we know what is Q in, right? So since we know what is Q in, we can say that for state 2 to 3, the Q in, so essentially here, this is Q in equals to delta U, right? So Q in is equals to U3 minus U2, and for constant specific heat, we can change U3 delta U to Cv delta T. And this one is just something extra, like you don't really need to do this also again, because the question didn't really give you a specific value. So if you are just taking the value from the table itself, then you just take a Cv value also. But again, just a reminder lah, if you have so these 4 terms are related. So if the question gives you values for either 2 of them, then you should be able to find the other 2. So if the question gives you a specific value rather than telling you to just assume from the table, then you have to find the other two. If let's say the question gives you the two value, okay? Because sometimes I will give, for example, in CP instead of 1.005, I will just say use 1 because it's easier that way. So then in that case, you should just follow that. Okay, in this case, you don't really need to because the value will be the same as table A2. Alright, so from here, if so you have QH in, you have CV, then you will have T2, so from here you will have T3. It doesn't really matter whether you use that Kelvin or degree Celsius for this particular question. Okay, but since we found T2 instead of Kelvin, so T3 will be in terms of Kelvin as well. So of course, T3 is not what we are looking for. We are looking for P3 actually, because that's what the question wants. So then in order to find P3, we can use ideal gas relation, so PV over T equals to constant. Since volume is constant here, so P over T equals to P over T, you can sub in all the value that you know T3, you know T2, you know P2, then you can get P3. So you have these three values. Right, so a lot of the time when you're dealing with constant specific heat type of question, and also you're dealing with ideal gas, when you're stuck, just think of ideal gas law or relation. Most of the time they are applicable, like in this case. Alright, so now that we have P3, so we have found P3, the next thing that we need is actually T4. So T4 actually follows similar logic. So 3 to 4 is a constant pressure heat addition process. So here we have unknown T4. This time P4 is no longer unknown because it's just P3, but again, it doesn't really help us much there. So this case, once again, we know what is Q in. But don't forget that for the constant for constant pressure heat addition, we have boundary work here. So with the addition of boundary work, we convert the whole thing into delta H. So this part of the process is a slightly different process. So all the other process, 1 to 2, 2 to 3, 4 to 5, 5 to 1, they can all be found through the change in internal energy, except for this particular process, because there is a slight boundary work there. So here we need to use delta H instead. So delta H will be Cp delta T. So from here you can get T4. Okay, so just a repeat. So let's say you want to find work in, you can actually find this through U2 minus U1 as well. If you want to find work out, actually the value you should be able to find through U4 minus U5. The value should be the same. It's just that most of the time we don't, because for the thermal efficiency equation, if you are to use work net out, then you actually need to find one more thing lah, basically. But essentially it's the same thing. Okay, so again, complete diagram for this, let's say this will be Q out, then this will be work in, this is work out. So this will be the more complete diagram. If I ask you to draw in the exam, what I'm expecting is actually the more complete one. So you need to include all the Q and the work. Okay, so then now we have the temperature for state 1, 2, 3, 4. And also we have solved the first two parts of the question, which is to find the maximum pressure as well as temperature. Then we move on to the last one. So we need one more temperature, which is T5. So we move on to process 4 to 5, isentropic expansion. So from 4 to 5, since it is isentropic process, so this is a keyword, this is isentropic process, then we do the same thing as 1 to 2. Okay, so state 1 to 2 we also do this, right? But now, unfortunately, there is one issue here, which is so we have T4, but we don't actually have V5 over V4, because compression ratio was V1 over V2, sorry, V2 over V1. It wasn't V4 over V5, and now V4 is not equal to V2 anymore. Okay, so then what we need to do here is actually, again, we need to use we need to find out what is V4 first, which, or rather we can find the entire ratio lah. So this might look a bit complicated here, but this is actually just PV over T equals to PV over T actually. Maybe I need to have a better way to write this. Okay, so we know that V5 over V4 is V1 over V4, because V5 and V1 is the same thing. So it's just that we are rewriting this T1 equals to V4 P4 over T4. That's all. Okay, so we are rewriting it in this sense. And we know that P4 is P3. Then from here we get the ratio for V5 over V4. Okay, so then from there, so you submit the value, then you can get T5, temperature for 5. It is still the ideal gas relation. You submit into this. Of course, if you want a simpler form, then you can actually just use PV equals to nRT, then you find each of the V, then you divide. It's also the same thing in the sense. But in that case, you get 4. Yeah. In that case, you will get small v, but it doesn't matter. Same. Okay, so now that you have gotten all the temperature, then you can find the thermal efficiency by using this equation. So for this equation, again, you can either find work net, which is work out minus work in, which is also actually Q in minus Q out, which is why we can simplify the equation to this state. So either way is fine, whichever one that you are comfortable with. So like I said, if you use work out minus work in, then you need to calculate one more extra thing, that's all. So considering heat rejection from 5 to 1, then once again, we have U5 minus U1 equals to Q out. Then you can find the Q out. Then thermal efficiency will be 59.5%. Okay, so just a short summary for this chapter. So okay, like I said, if let's say you are dealing with constant specific heat question, just a quick summary lah. If you have no idea what to do, find all the temperature at all states, because as you can see here, we make use of T1, T2, T3, T4, T5. We need all of them either way. So for variable specific heat question, then you look for all the internal energy. But of course, with the exceptions that, yeah, if you have constant pressure heat addition, then you find enthalpy. But otherwise, you will make use of internal energy at every state. Okay, the exception I'm not writing here, that one you study yourself, because I also don't know how to write it in here. But this is just a general way of solving this. You look for all the temperature, you look for all the internal energy. So if you want to be safe, then you look for all the enthalpy also, but then you won't be making use of all of them lah. That is only useful in the constant pressure heat addition. Okay, maybe this way. Okay, so is everyone done with this? Anyone still need this slide? Alright, okay, so actually we're done with this chapter. So summary here, basically here the main thing that you have learned is actually, so of reciprocating engines, and then you learn about Otto cycle, diesel cycle, how we combine them, and we make use of air standard assumptions for our analysis, and then how you analyze all these four cycles. The two cycles. Okay, so these two cycles are the more basic type of cycles. Okay, now then we will move on to our final chapter actually. Okay, so for anyone that still needs a code,
这个看一下，我们下一个，啊，影响影响，影响看表面，表面多呢。就会真的是。
Maybe you copy down first. Then by the end of the class you cannot, then you let me know. All of you also cannot join. Okay, never mind, we finish this one first. Alright, we enter the final chapter today, even though we are at week 11. Okay, so while we are on this topic, again reminder, next week class I won't be replacing. So because we are at the final chapter now. So that you will see that in your timetable it should be on this Saturday, the replacement class. Don't go, okay? It's just for me to replace on paper. Okay, please tell your classmates they are not here. We are not replacing next week's class. Okay, if they see the Saturday class, don't go. Holiday what? Next week is holiday. In case you don't know. Monday and Tuesday, both days. One is Malaysia Day, the other one is I forgot. Our Muharram or something. Okay, so we're in final chapter now. A slightly more exciting cycle compared to the previous one because this one I can play more things. Okay, so this chapter comes out every semester. Make sure you know how to do. But for some reason, every semester for this question, I will either get full marks or less than 10 marks. So make sure you learn properly for this chapter. But I can ask a bit differently. You will see in. So like I said, after I finish the syllabus, I will proceed to past year. So you will also see some of the questions that I've asked before this. Okay, so here we are talking about vapor compression cycle here, which is a refrigeration cycles. You sort of have learned about this in your lab, and also we learned the basic in the thermodynamics second law. So now we look at this in more details here. So objectives here, for this chapter, we will introduce you to the concepts of refrigerators and heat pumps and the measure of their performance. You have learned this, right? COP. So then we will analyze what we call the ideal vapor compression refrigeration cycle, and then we will also analyze what the actual vapor compression refrigeration cycle. Actually, it's a lie, it's not exactly an actual one. We still make some idealization, but again, close enough. And then we will review the factor involved in selecting the right refrigerant for an application. This is more theory. Then we will discuss the operation of refrigeration and heat pump systems. Then we will see some form of innovative vapor compression refrigeration system, meaning how we can modify them further so that it becomes better or it fits a different purpose. Then lastly, you will see what is called an absorption refrigeration system. That one is just a concept. We won't really analyze it in detail. Alright, so let's look at the first part, the basic thing first. So like I said, you have learned this. So refrigerators and heat pump, they are the same thing. Okay, this is a system that transfers heat from a low temperature region to a high temperature region. So something that in a way goes against thermodynamics second law. Okay, because we are transferring heat from a low temperature area to a high temperature area. Usually we do the other way, right? And how do we do this? So this can only be achieved with this additional work in that we supply to this system. So without this additional work, obviously this cannot happen because in a way it goes against the second law. So this work in helps you to bring the energy power level higher so that it can go to the higher temperature side. That is the basic idea of this. So a refrigerator is a device used to keep a space at a low temperature side, while heat pump is used to keep a space at keep the temperature at a high temperature side. So they are the same thing, but their target is different. Basically that. Refrigerator, the target is the cold area. We are removing heat from the cold area. The heat pump, the target is the hot area. We are using it to heat up or keep the temperature at the high temperature side. So we are supplying heat. So heat pump supply heat, refrigerator removes heat, but they are the same device, just different target again. So COP is used to measure the performance. Again, you have learned this. So the COP, the equation is essentially the efficiency equation, but slightly different in the sense that they are still desired output over required input. In both cases, input is work in. But heat pump, like I said, the job of the heat pump is to supply heat. So QH or Q out becomes the output in this case. While for refrigerator, the job is to remove heat. So QL or Q in is the main focus here. So we know that COP of the heat pump is basically just COP of the refrigerator plus 1. Okay, if you analyze based on the Q and the equation that is just QL and QH, then you will see that it is actually just COPR plus 1. If provided that, of course, these two doesn't change. Okay, don't change. Okay, and for COP, for both COPR and HP, the value can be more than 1. And in most cases, they are actually more than 1. Except for your lab. Your lab, the actual one, you don't really get more than 1. But then you also know that the value there is not actually accurate because of some of the way that we measure. Right? So, yeah, your lab report, there's still one group that is not due yet, right? Or due this week or something like that. So, yeah, I will finish marking and send back to you once the last group has submitted. So for now, I'm just keeping them. Okay. So the refrigerator cycle or heat pump is actually modified from the reverse Carnot cycle. Okay, so Carnot cycle used for power generation is called Carnot heat engine. So the normal Carnot cycle that you learned is actually used to generate power. Okay, so this was also something that you saw before this. So the normal Carnot cycle consists of a turbine, a condenser, a compressor, and a boiler. So even though this is an open system, but you can see that it actually undergoes the same process. I mean, if you don't consider all those isentropic, isobaric term, you can see that it actually undergoes similar process to what you learned in Otto cycle and Diesel cycle, because you have a work-in process here, compressor. You have a Q-in process here, boiler. Then this is a work-out process, expansion process. This is a Q-out process. So you can see all the heat generation or all the power generation cycle follows the same concept because most of them are derived from or modified from the Carnot cycle. Okay, that's why they undergo the same type of processes. So for reverse Carnot cycle, as the namesake, it goes in the reversed direction or the opposite direction. So a reverse Carnot cycle can be used to provide cooling or heating again. And it is called a Carnot refrigerator. So you can see also that's why it's called reverse. So Carnot cycle, we use heat to generate power. Reverse Carnot cycle, we use power or work to generate heat or to remove heat. So reverse Carnot cycle, you can see same thing but opposite direction. Of course 1, 2, 3, 4 we change the term as well lah. But it's actually just the same thing but the reverse direction. So in a typical reverse Carnot cycle, in a typical reverse Carnot cycle, it should consist of actually the same thing. So now we have a compressor, condenser, turbine, and evaporator. Actually still same thing, but we go the opposite direction. So this time evaporator goes to compressor, compressor goes to condenser, turbine, then back here. So again, this is just the reverse Carnot cycle. Of course, the actual one is not this way. Okay, so the reverse Carnot cycle, just like the Carnot cycle is the most efficient cycle operating between TL and TH. So reverse Carnot cycle will be the most efficient refrigerator cycle operating between TL and TH. So this will be the benchmark for refrigerator cycle when you are designing refrigerator cycle. So you use this TH over TL equation to benchmark how well your refrigerator is performing or how close it is to being the optimum performance. This is the optimum performance. This is the best one. So now, this is the most efficient cycle, but there is one issue with it. You can see from what we write there. It is impractical during process 2 to 3. So this process is not practical. Why is that the case? Because remember I mentioned, we generally say that pump is for liquid, compressor is for gas. We don't actually have anything that works in between. Because it doesn't make sense also. You want something that is compressing both liquid and gas at the same time. So you can see based on this, 2 to 3, if we are sticking to a Carnot cycle, process 2 to 3 actually will involve compression of liquid vapor mixture. So it's not practical. You want it to either compress liquid or gas. Process 4 to 1 is also not very practical because it is an expansion of low quality liquid vapor mixture. So what do we mean by that? So you can see this process. If we go by the usual way that we go, this is a turbine, right? So we call this part a low quality liquid vapor mixture. Why is that the case? Because because you have learned that what is quality? Anyone? What is quality? Quality is the fraction of the vapor in the mixture. So the higher quality of a mixture, the more vapor you have, meaning the closer it is to being a full vapor. Low quality would mean that it has a lot of liquid droplet. It will have a lot of liquid component in it. We don't want that to be pushing our turbine. Why is that the case? Because it will lead to corrosion. Very simple. The gas that is pushing, so you are sending the mixture to move the turbine, and then if it has a very high liquid content, then the turbine will get corroded very fast. Then you need to keep replacing it. So it is also not a practical process in this case. So these are the two things that are not practical that we want to eliminate, right? So what we do here is very simple. Since these two are not what we want, we modify these two parts. So the vapor compression refrigeration cycle is the ideal model for refrigeration system. So here we are focusing on TS diagram rather than PV diagram, because we are mainly dealing with heat here. You can see actually when it comes to cycle, a lot of the time we actually will focus a lot more on and also the open system version will focus a lot more on TS rather than PV diagram, but you need to know for both of them. So the refrigerant, in this case you can see, refrigerant is vaporized completely before it is compressed. So very simple. At the compression side, since we don't want it to work with mixture, we just push the whole thing over. So you make sure that it is vaporized completely before it goes into the compressor. That is the first step. So the other one, so for the turbine side, no matter how, you can't really eliminate the moisture problem because the only thing you can do is push it further, then it becomes fully liquid. And we cannot eliminate the phase change thing because that is what we want to absorb and reject heat, because phase change involves the highest heat transfer. I think this one you guys know even from secondary school. So of course turbine is still applicable in most cases. We will talk about it later. So now instead of using a turbine, because here, let's go back here. What is the main function of the turbine here? The main function here is actually we want to bring state 4 back to we want to bring the pressure back down as well as the temperature. Turbine main function is actually to generate work. or power, which is not something that we need in this case because you don't need the system to generate power. So we replace it entirely with throttling valve or expansion valve or a throttling device. These are the example. Again, things that you have learned in your lab. These are the two things that you learn actually. Capillary tube, and also your TV is thermostatic expansion valve. So same thing. So we replace it with a throttling device. So what does a throttling device do? Throttling device is basically just throttle the flow so that the pressure drops and at the same time the temperature drops. And thus it managed to achieve the same thing. So the actual process here, so here you can see that in this case, then TS diagram become a new process here. Okay, let's just have a look at all the process first. So now, based on this, process 1 to 2 is an isentropic compression. 2 to 3, as usual, is a constant pressure process, constant pressure heat rejection process. 3 to 4 is throttling in an expansion device. 4 to 1 is a constant pressure heat absorption in an evaporator. So now this is the four processes that we have. These are the processes for an ideal vapor compression refrigeration cycle. So this is the most widely used cycle for refrigerators, aircon system, and also heat pumps. So most aircons, especially the one at home, basically just works based on these four things. This is actually an actual representation of how it works. So unlike ideal cycles discussed previously, so you may also notice that for throttling process, it cannot be an isentropic process. Why is that? It cannot be an isentropic process because you will definitely get some losses, no matter what. Because throttling is just a change in the flow. You are just causing a change in the flow through maybe a change in the size of the pipe, for example. So this is not a reversible process, since it is not an isentropic process. So in a way, it also means that it is irreversible. So now, normally, let's say it's in the turbine, when we say it is reversible process, okay, of course we know that reversible process also don't happen in real life. But let's say if there's no losses, what we are saying is for reversible process, if this substance is moving the turbine and generating this much power, if we move the turbine with the same amount of power, it can change the substance back to the initial state. That's what we mean by reversible process. It can go both ways. But in the throttling process, that's not what happened, because in throttling process, the change in the pressure and temperature is a result of energy loss without anything that you do, meaning the loss is by default. So you cannot just let it flow back and then it can't go back to the same state with the same amount of energy. Basically, that's what we are saying here. So now, the question will be here. You will see that actually, to be fair, we can still use back a turbine, right? It won't eliminate the moisture problem that we mentioned. So it won't eliminate the low quality mixture problem that we mentioned. But technically speaking, the cycle can still work, right? So then why don't we do that? Since, what's the harm if we have a turbine over there? We can generate more work, maybe we can use it for other purposes. And you can reduce the work in because you are generating some work out. So your work net is lower. But we don't really do that because for the main reason is that, you see, 3 to 4 is a throttling device, meaning you have seen this in the lab. Throttling device is simply just a pipe. If you look inside, then you will see that the cross-section area is different, that's all. So that is a throttling device. Compared to having a turbine where you need to purposely do piping to control, to channel the flow to a turbine and work it, and then the turbine has a potential of being corroded, the benefit of generating work is not worth the effort, basically that. to place a turbine over there. And also, again, we know that work is basically dominated by P and V, right? So V over here is a very low number value. So meaning this work that you get is actually very low. So once again, not worth the effort lah. That's why we just use a throttling device instead. So throttling device, basically when the flow goes through it, it gets expanded, and through some of the losses, then it get, again, ideally there's no losses, but yeah, it's an expansion process, so pressure drop, temperature drops. Okay, so step 4. So if let's say if we actually use an isentropic turbine, then the graph should go directly down. Then it shouldn't go this way anymore. Okay, that is provided if we use an isentropic turbine. Okay, so these are just some of the examples of where we use a refrigeration cycle. So you can see an ordinary household refrigerator. So this is the older style one where the freezer is on top and then the other component at the bottom. But these days I think a lot of the refrigerator goes the other way around. So the freezer at the bottom, but the concept is still the same. So you can see condenser coil. So you can see compressor is over here. Then it goes through the condenser coil. Then capillary tube. Then evaporator. Then after that it goes back down to the compressor. So that is the full process. So again, as I mentioned when we were talking about this in lecture 7, don't push your refrigerator all the way to the back. Actually, in that case, don't push any electronic devices all the way to the wall, because that's where they are releasing heat. So same thing for TV and stuff. Okay, but of course those won't have as much heat rejection compared to this, because this you are removing heat intentionally. So you must always leave some space. Okay, then this is just an ordinary. So and then here we won't see in Malaysia, it's just a heat pump for household purposes. So you have seen this in the lab. This is normal capillary tube. This is the TV. And this is condenser coil, evaporator coil. So these are the two units for aircon essentially. So if you go to a, let's say aircon industrial, if you just look through their workshop, their evaporator and condenser basically just look something like this. So at aircon industrial, we just refer condenser and evaporator as coil because that's what they look like, and they are the same thing. They work similar, just the opposite way. So they are just both coil. So outdoor, what we call is outdoor coil, indoor coil. Okay, let's see how we analyze this. So ideal vapor compression cycle involves an irreversible throttling process to make it a more realistic model for actual system. So you have learned this in the lab as well. For the similar way where we analyze Otto cycle, diesel cycle, if you just, so this is open system. So if you just go through Q minus W equals to delta H, because I said open system, you will see that all the heat changes and all the work changes is just the change in enthalpy. Okay, so this will be the equation that you use. So QL is actually just H1 minus H4. Work net in is H2 minus H1. Then QH is H2 minus H3. So again, keep it to positive value. That's all. Or else, if you use, because again, if you use after minus before, QR for R no issue. But this one, if you use after minus before, you will get a negative value. Then your COP somehow will become negative. So keep it to positive value. Okay, now, so for ideal refrigeration cycle, this is saturated vapor, and this point is saturated liquid for the ideal cycle. Okay. So by default, you should know these two. The question don't have to tell you that. And then, yeah, which also means that if you're just given the pressure limit for both levels, you can find a lot of things here. because you should know that this is saturated vapor, this is saturated liquid. So you can see H1 is Hg at P1 or T1. Then H3 is Hf at P3 or T3. So this is the TS diagram, and here this is the PV diagram. Both of them are equally useful, meaning like both of them has its own use, but most of the time I will ask you to draw TS diagram because it's easier to analyze for you. But if you go to industrial, sorry, this is pH. They will most probably ask you to draw pH diagram instead. I mean, industrial, they will measure lah, but then actually not accurate also, because they also assume that it's ideal. So this is the shape that they are looking for actually. Let's say if you are in industry, at least based on experience lah, at Daikin lah. Other places, I'm not very sure whether they use pH diagram or not. Okay, so this is how it looks like. So based on this diagram, you can actually analyze this again very easily just by knowing the pressure limit, so the upper limit and lower limit. How do we do that? Let's look at one example. So this example, you can see it only tells you the two limit. So a refrigerator uses R134A, so keyword R134A, you need to use R134A table as the working fluid and operates on an ideal vapor compression refrigeration cycle between 0.14 and 0.8 megapascal. So you have one pressure limit here, two pressure limits. So the high pressure, low pressure. If the mass flow rate of the refrigerant is 0.05 kilogram per second, so you are given mass flow rate as well, but of course this is independent, because without it, you just find the small q. With it, then you can find the capital Q dot. So A, you need to find out what is the rate of heat removal from the refrigerator space and the power input. So you are looking for QL and work in here. Rate of heat rejection, then you're looking for QH, then after that COP. Basic question lah, so ask you to find everything. Okay, so we can look at how we analyze this. So we bring forward this diagram over here. So like I said, common practice for us, we usually will draw the diagram because it will enable you to analyze it easier. In your cases, most of the time you don't have to draw the 4S diagram, the 4S path, meaning this path, because it is not really a useful path unless the question has its own idea lah. Okay, so assumptions as usual. I forgot to ask you this, but refrigeration cycle is, what kind of system is refrigeration cycle? Refrigeration cycle is an open system. But what kind of cycle it is? Closed cycle or open cycle? It is a closed cycle. In terms of cycle, it is closed because the refrigerant, by right, should recirculate inside infinitely. Meaning, technically speaking, we don't actually have to, change gas. The one that at home your parents probably will say this. Technically speaking, ideally we don't need to do that. But of course, through piping we always have leakage. So the refrigerant will get less and less over time. So every few years you should change the refrigerant from time to time. Okay, so since this is an open system, you must have this assumption. Okay, steady operating condition, meaning we are talking about steady operating condition will also means that you have a steady flow system. Steady flow system, we only talk about one type usually. So now the whole thing is steady. So we say that steady operating condition, so this is the assumption that you must have. Then KE and PE are negligible. Our typical assumption. Okay, so then we can start analyzing. Now, when you start analyzing, you can either start from state 1 or state 3 because these two are independent. So like both sides they are assigned. Of course here, very straightforward because it's an ideal cycle. In exam, you look at what information is given to you. Okay, so we see here. So we know that P1 is 0.14 megapascal. So we know that, since we know this, then we know that H1 is Hg. While we are at it, we also look for S1. Why is that the case? Because now from state 1 we move on to state 2. Ideally since this is the ideal cycle, we know that 1 to 2 is isentropic process. So for isentropic process, S2 is equal to S3. That's why here S3 equals to S1. That's why here we look for S1 first. Then we compare the table for S1 value and pressure 0.8 megapascal to see what is the H2 value. So this is not most probably, you just look at the diagram, you will know that this is a superheated state. Right, so if you check the superheated R134A table, then you compare, you get the H. I think by now I don't really need to show you this anymore, right? You should know how to find. So you have two value information, you have 0.8 megapascal, you have S1, then you can find H2. Most probably interpolation is involved here. So now we are settled with the right hand side. Then we move on to the left hand side. So we know that P3 is 0.8 megapascal, H3 is HF, then 95.48. So this one again from the table. Okay, so then we are left with state 4. How do we approach state 4? So for state 4, this graph itself actually, this TS diagram is not so useful, because if you just look at this graph, you actually cannot see how to link them. But you have done your lab, and we also have pH diagram here. So based on pH diagram, you can see that H3 is equal to H4, right? So we can just say that. Okay, so from here, now you can see the similar formula from when we solve Otto and Diesel cycle. So for this cycle, if you do not know what to do, try to find all the enthalpy. Essentially that. Once you have all the enthalpy, then you have enough information for everything. Mostly. Okay, so now that we have found all the H, so you can see that we have H1, H2, H3, H4. Then you can see we actually haven't started solving the question yet. So now we look at A. So the rate, which is why, just like your test, because I think some of you asked me during the test as well, sometimes you might see that the marks that I give you don't really tally with your A, B, C, D, because sometimes we do something first, sometimes some students will do something later. For me, I will just mark in general. If, of course, you don't try to fly around too much, because it gets very confusing for me also when I mark. But in general, if you do something that I want later, I will still give you mark after that. So it might not be tally 100%, just like this, you see. We haven't even started A, B, C, D, but they found a lot of things already. Then I have to start marking first, right? So same thing. So A asks for the rate of heat removal and power input. Then very straightforward. QL is just m dot H1 minus H4. So don't forget the mass flow rate, because we want it in terms of power or rates of heat removal. So we want it in terms of kilowatts. Then work in is simply m dot H2 minus H1. Then B, rate of heat rejection, H2 minus H3. So it could also be determined from QH equals to QL plus work in, because we know that E in equals to EL. So we learned this from the second law, during the second law chapter as well. So after that, COP is simply this. Okay, so far so good. Quite simple, right? Until now. But of course, it's not going to be so simple lah. So otherwise there's a reason why thermal failure rate is not so good, right? Okay, so this is the basic version. Now we look at the more complicated version. So the basic version is the ideal vapor compression cycle. Okay, so this will bring back to something that I mentioned about the previous chapter. Remember, I said that actually when we talk about cycle, ideal cycle is not equal to Carnot cycle. You have to differentiate these two. So when we say ideal, we are saying that in this form, it is the most ideal version. But it is still not Carnot cycle, because Carnot cycle will always be that square when you draw TS diagram. Okay, so Carnot cycle will have the highest efficiency. Ideal will come after that. Then we will have what we call actual refrigeration cycle. Okay, so just now, even though it is ideal, just now the ideal cycle, we still make a lot of assumption about a lot of idealization. So in actual, the vapor compression refrigeration cycle will differ from the ideal one due to, again, irreversibilities, things that you learn. The main thing will be due to fluid friction, which is the pressure drops in the pipe. Which will cause pressure drop in the pipe, so you will have some losses. And also you will have heat transfer to or from the surrounding, depending whether it is during the hot side or the cold side. So let's say during lab, when you get bored, you're observing it, then you keep touching the pipe. That actually is also one of the things that will cause more losses to the flow, because you will be either transferring heat to the system or you will be taking heat out. So the COP will decrease as a result of these irreversibilities. So difference here. So on the left is the one that you see is the ideal one. On the right is actually how it will look like if you are dealing with an actual one. So the differences will be, first, compression will no longer be isentropic. Second, the superheated vapor, you will get a superheated vapor at the evaporator exit, most likely. So this one, now, so if you don't control it properly, it can either be a mixture, meaning a very high quality mixture, or it can be superheated. Which one it is? Actually, it depends on how it is being designed. But of course, for let's say if you are an engineer, if you are to design this, you cannot design like exactly. Of course, you want to push it all the way to the end because you have a compressor. You want the compressor to work with the vapor. So of course, it is better that it comes out as a superheated vapor at the evaporator exit rather than a high quality mixture. Because high quality mixture, then you will still have some form of liquid. Then, at the condenser exit, you will get a subcooled liquid. This is also most likely the case. Mostly you won't try to get a mixture. You will try to get a subcooled liquid instead, meaning compressed liquid. Then after that, which is also the case when you did your lab, you will see that you draw all the way to the other side. So lastly, pressure drops in condenser and evaporator. So this is something that will definitely happen. As long as you have piping, inside the piping you will have friction. So the fluid that flows inside will always experience pressure drop as it flows through the pipe. So which is why in the end, the graph looks something like this. So you can see that this pressure drops, this pressure also drops. And this is the non-isentropic part. So this is how it looks like for the actual case. Okay, so comparison. Carnot refrigeration cycle on the left. So this is how Carnot will look like. This is how ideal refrigeration cycle will look like. And then this is how the actual refrigeration cycle should look like. So again, if we are talking about efficiency here, this will be the highest, then followed by this, then followed by this. So this is the Carnot. this is ideal, this is actual. So important question here. Do the area enclosed by the curves here give us the net work output of the system? For all three. For Carnot refrigeration cycle, yes or no? Because we always say, remember when we study about heat engine, we always say that area under the curve or area enclosed by the cycle is the network, right? So for Carnot cycle, is this the case? Yes, right? How about the other two? The other two, the answer is actually no. The main thing is because of this thing. Because of the throttling process. Because the throttling process, they are unknown. Okay? So the area enclosed, like in this case, Ts, you can say that safely because QH minus QE. So like QH minus QL. So this one. Then you get work net. But in this case, ideal refrigeration cycle and actual refrigeration cycle, that is no longer the case because of that throttling process. The throttling process is not reversible. So you cannot assume that it is reversible. Then ultimately you don't get a work net. Or if you just think for a simpler explanation, there's no work out here lah. You only get a work in. Then that one is just throttling. So you don't actually get a work out, so you don't get a net work output also in that case. So that's the simpler way to look at this. Okay, so here you get to see a comparison between these three cycles. So Carnot is something that cannot happen. Ideal is what we modify from the Carnot so that we can make use of this cycle, but it's still ideal version. Then actual is what you get in actual. Now, what if I ask you to analyze this actual refrigeration cycle? Do you think it's possible? Actually, it's not. Okay. Now, if you are to analyze the actual refrigeration cycle, you will see that a lot of the things that you learn will no longer be applicable because the pressure drops everywhere. Temperature, you cannot predict the pressure drop also. Technically, you can. You need to calculate a lot of things. The mechanical guy should know that if you want the pressure drop. So the easiest way, let's say, if you want to analyze the pressure drop is, to analyze the actual cycle is, you measure temperature and pressure here, you measure temperature, pressure here. So you need to have a probe at every location in order for you to analyze this, which actually is not really very feasible also, because then you need to put everywhere. So actually, even at industrial, most of the time, if they are testing a device, let's say they are testing an aircon, they also won't do this. They won't be measuring every single point this way. I mean, temperature, yes, because you still need to measure, but the pressure-wise, no, because it's very troublesome. So what they do here is, we still do some idealization, but it won't be the actual, it won't look like this lah. So what are the idealization that we will do for the actual cycle? It's actually something that you did in the lab as well. So in the lab, do you remember that there are still two things that we kept constant? What do you measure in the lab? You measure all the temperature as well, right? T1, T2, T3, T4. Pressure, you don't remeasure. Pressure, you assume that they are constant. Meaning you assume that you have the two pressure level, then that's all. We assume that the pressure still don't change. So meaning you assume that the flow is not so viscous, so there is not much pressure drop. We assume that they remain the same. So then in that case, then it is easier for you to analyze. So that that efficiency, then let's say if you assume pressure is constant, then the efficiency will be somewhere between here. So let's say if you do that analysis where you assume pressure is the same, then it will still be the efficiency that you analyze would, or rather COP, sorry, actually I should use COP, not efficiency here. Someone should remind me this. This is actually COP, sorry. So COP. So the COP that if you assume pressure is constant should be between the ideal and the actual one. And to be fair, it won't differ too much. Usually the difference is very little. Okay, so now my slide don't really have that actual one, but we do have one example on that. Let's look at one example. Okay, so this example, now example 1, so actually technically example 2. A refrigerator uses R134A as the working fluid and operates on the vapor compression refrigeration cycle. Why are there so many typos here? Okay, so now let's say we go back to the previous question. You see, this question says ideal vapor compression refrigeration cycle. So you can just assume that it is ideal. If the question, like in this case, never mentioned ideal, so ideal is not mentioned, you cannot assume that it is an ideal cycle. So even if it is, you still need to figure out based on the information that is given to you here. Okay, so if the ideal term is not mentioned, then you cannot assume that it is an ideal cycle. Now, sometimes I will use this term. Wait up. Okay, so simple vapor compression cycle is still not ideal. It just means that we don't have any modification to it. The configuration itself is still the most basic one. But it is not ideal. Okay, so this one you need to remember. A simple vapor compression cycle is not an ideal cycle also. Okay, so main thing, as long as the question doesn't say that it is ideal, you cannot make all the ideal assumption. None of them. Okay? So you have to get information from the question. So we look at the question. The evaporator and condenser pressures are 200 kilopascal and 4,400 kilopascal respectively. So remember just now I mentioned, so the pressure will still remain a constant. So in this case, let's say we draw TS diagram. These two constant pressure line will still remain constant. Okay, so you will still get 200 kilopascal here, you should still get 1,400 kilopascal here. No change here. So no pressure drop. We are still assuming this. So the isentropic efficiency, so something from chapter 7, you get what you call an isentropic efficiency in this case of the compressor is 88%. So we know that the isentropic efficiency of the compressor is 88%. So the refrigerant enters the compressor at the rate of, so you have mass flow rate 0.025 kilogram per second. Superheated by 10.1 degrees Celsius, so it's a bit of a complicated term here, and leaves the condenser subcooled by 4.4 degrees Celsius. So we know that when it leaves the compressor, it is at superheated state. That's why it's called superheated by 10.1 degrees Celsius. And when it leaves the condenser, it is subcooled by 4.4 degrees Celsius. So determine the rate of cooling provided by the evaporator, the power input and the COP, and the same parameters if the cycle operated on the ideal cycle. So A asks you to calculate the rate of cooling, meaning QL, the power input, work in, and the COP. Then B asks you to recalculate everything for ideal cycle. Okay, so let's say, how do we draw this TS diagram in this case? We know that state 1 is supercooled, meaning after the evaporator is superheated. So 1 should start somewhere here. So this is your state 1. Since we are dealing with an non-ideal cycle and actual cycle, and also you can see the question says that the compressor have an isentropic efficiency of 88%, meaning that 1 to 2 is no longer an isentropic process. So this cannot be a straight line anymore. It has to go somewhere to the right, because entropy is always increasing. In that case, if you can think about it this way, so it's always, it will go somewhere to the right. So 2 is here. You can also draw one more line, dotted line here, and call this 2s. So 2s will be if, let's say this is ideal. Or 2s is also if it is isentropic, but in this case this is not isentropic. So 2. Then 3 is subcooled, so 3 is somewhere here. Then 4 somewhere here lah. So 4 is usually the more ambiguous one because we don't really know where it is. So we just draw. As long as it is at the mixture side, then that's fine. So it will look something like this. So for now, actually you don't need to look at this one first. Got a nicer looking one here. Maybe resolution not so high, but slightly nicer looking than my handwriting, I hope. Okay, so same thing. Alright, so how do we analyze this? Actually, the step is still the same. Okay, step is still similar. So from the refrigerant 1348 tables, we know that at 200 kilopascal, okay, at 200 kilopascal, the saturated temperature is negative 10.1 degrees Celsius. Okay. So if we look back at the question just now, it says that at state 1, the refrigerant is superheated by 10.1 degrees Celsius. So what do we mean by it is superheated by 10.1 degrees Celsius? Meaning, it passed the saturated temperature by 10.1 degrees Celsius. That's why it says superheated by 10.1 degrees Celsius. So it is higher than the saturated temperature by 10.1 degrees Celsius. So meaning T1 is actually 0 degrees Celsius in this case. Can you understand that? So the saturated state is this temperature. If it is superheated by 10.1, meaning it is higher than the saturated state by 10.1. So here we just add it on in. So then from here, you make use of the superheated R1348 table. You look for 200 kilopascal and 0 degrees Celsius. Then you can get H1. You can still note down S1 first at this moment. Okay, so again, it might not be very clear what you need now, but you can note down first. Okay, so this is P1, T1. So unlike the previous question, so now we no longer assume that this is a saturated vapor. This is superheated vapor, okay? Or superheated R1348. Okay, so then now we go to P2 first. Now, we know that P2 is 1400 kilopascal. This one won't change. So whether we are dealing with 2S or 2, it is 1400. But for S2, for state 2, we don't know anything yet. This one actually, it should be S2S. Okay, this is not S2, sorry. Missing term. It should be S2S equals to S1. S2 is not equal to S1 because S2, the actual process is no longer isentropic. So S2S is equal to S1. So from there, you can obtain H2S. So this step will be the same as the ideal side. Okay, so this is for the S2S, not for 2. Okay, so for some reason we are skipping. Okay, this step not so good. So never mind, we put here first. Okay, so this one is for H2S, not H2. We need H2, but apparently I'm looking for it later. Okay, so now we know that. So now we look at state 3 first. So at state 3, we know that the saturated temperature is 52.4 degrees Celsius. Then same logic. State 3 told us that it is subcooled by 4.4 degrees Celsius. So it is lower than the saturated temperature by 4.4. So if you minus it off, what you get is 48 degrees Celsius. So again, you have 1400 kilopascal, you have 48 degrees Celsius, but state 3 not too hard because you have compressed liquid or subcooled liquid. But we know that we don't really have a table for that. So we assume that this is approximately saturated liquid temperature. The properties of the saturated liquid. So H3 is approximately HF, but at 48 degrees Celsius, not 1400 kilopascal. Always remember, when you do approximation, we always approximate to the temperature, not pressure. T3, maybe. Okay, so now we got H3. H4 is the same. So for the whether we are dealing with an actual or the ideal, H3 equals to H4 is the same, again, unless the question tells you otherwise. If the question tells you, let's say, if it lose heat by, let's say, 10 kJ per kg, then you say pandai. But otherwise, it's the same. H3, H4 won't change. Okay, so now we have H1. We have H3. We have H4. We are still missing H2 because that is H2S, not H2. So what we can make use of is what you have learned, but you kind of forgot maybe, is isentropic efficiency. So you were given that isentropic efficiency is equal to 0.88. So for the isentropic efficiency of a compressor is the isentropic version over the actual version. Again, don't need to memorize this. You just imagine it this way. You are having a compressor. Whether it's actual or the isentropic one, you want to compress from 200 kilopascal to 1400 kilopascal, meaning you want to achieve the same outcome. So to achieve the same outcome, the actual one will actually require more power compared to the ideal one. So the actual one will be at the bottom, then the isentropic one will be at the top. So by using this, you can finally get the H2, the actual H2. So after that, then you can find QL, QH, work in, and then COP. Okay, can you understand? So again, reminder, if you're dealing with an actual cycle, don't make your own assumption. Everything must be taken from the question itself. So sometimes I might tell you it is saturated liquid, sometimes it might not, or yeah. So you have to start from whatever that I give you. So look for, so again, like this case actually is quite easy also, because state 1, state 3, we do give you 2 information. But sometimes maybe, let's say for example, I give you 2 information at state 4. You should start from the state where you have 2 information, then you go through. But ultimately, we are just rotating between these 4 states. So the way that you solve their relationship don't change. It's just that maybe the starting points is different. So you need to basically see lah, where are the starting points, and what are the information I give you. Okay, so now let's look at B. So A we are done. B we can go through very fast, because B is essentially just the ideal cycle. Okay, so when we solve for B, essentially we just make use of all the previously made assumption. So state 1 we set it back as saturated vapor. Then never mind, I just open all this. So state 1 we just set it back as saturated vapor. State 3 we set it back as saturated liquid. Then state 2 is the isentropic process, so this time S2 equals to S1, then you can get H2. So you get H1, you get H2, you get H3. And H3 is equal to H4. So the ideal version is actually the simplest version, because everything is very fixed. You just need to know how to read the table. Okay, then from here, you can see that we can calculate a new Q, H, and W, and then COP. So based on this COP, you can see that if we are assuming that this is an ideal version, or ideal vapor compression refrigerant cycle, the cooling load will be QL, because the job it is doing here is QL, has increased by 18.5, which is actually quite significant, not very close. But COP wise, if you just look at the COP increases by 5.9% if you assume ideal. So in a way, it is still not too bad in that case. They're still quite close. So this is just a comparison when we are looking at the ideal refrigerant cycle compared to the actual refrigeration cycle. Okay, so we will only continue with one more slide. Then heat pump I'll leave it to Thursday. Let's see. Okay, so one more slide actually is just full of words. So this is just about how do we select the right refrigerant. So several refrigerants may be used in refrigerant systems such as chlorofluorocarbons, these kind of things I think you have heard. So ammonia, hydrocarbons, carbon dioxide. Actually we do have different type of refrigerant. So air and water can also be considered refrigerant. But of course, though these are not the things that we use for normal commercial our residential purpose or commercial purpose, because like water, the boiling point is not low enough for us to be used at normal temperature, but in more how should I say, in more extreme cases in industrial, then maybe yes. Ammonia of course is also the best one actually, but it is toxic, it's not suitable for us, so then we mainly use them for industrial purposes. Now, so all these R here, the R11, 12, 22, of course they are a bit outdated, because if you just check through your advertisement, sometimes you do see like Daikin's advertisement, Exxon and stuff, they do tell you what refrigerant that they use. Not that it serves much purposes to you, because if you just look at the number, we wouldn't know what it is for, right? But yeah, sometimes you will see things like R34. Those are the newer one. This one we take from textbook. We don't really update this one because again not too important. It's just different value. But R134A is actually something that is very common. Okay. Even so, I think some still use them these days. Then, but otherwise, yeah, we don't really use them too much anymore. So all these are just trivia. So then, I think CFCs, we know what they are also, right? So CFCs allow more ultraviolet radiation into the Earth's atmosphere by destroying the protected ozone layer. That's why we don't really use much CFCs anymore. So these days it is more on, what do you call that, HCFCs I think. And also, yeah, so refrigerants that are better or more friendly to the environment. So when you consider the right refrigerant, two important parameters will be the two temperature, meaning the TL and the TH that the refrigerator system is going to work at. Because you want it to be able to evaporate. Like once it evaporates, the temperature is higher than the T. Once it evaporates, before it evaporates, it needs to be able to evaporate at the TL side, and it needs to be able to be condensed at the TH side. So that is the main consideration, the two parameters that you need to consider when you are selecting the refrigerant. So one more extra thing here. Now, so we talk about how refrigerants destroy the environment, right? Like when we use aircon, it's not so environmental friendly. But technically speaking, when you are using your aircon, it doesn't really pollute the air in a way, because what comes out from the aircon is actually just air. You are cooling it, you are taking in your environmental air, we are cooling it down, then you are blowing it out. So like I said, in ideal cases, our gases don't leak. All your refrigerant don't leak. So actually that won't actually happen. It won't actually affect the environment too much. The main problem will be when you are changing the gas, because we just release them to the environment. But when you are using them, actually the cold air itself doesn't really, it's not the main pollutant. It's not a pollutant basically. But of course, the more you use it, the more leakage there will be. That one quite common sense. Okay, so yeah, don't be afraid of using them since you're gonna service it anyway. Alright, so this is where we stop. Next will be heat pump, and then heat pump same thing. Then after that we will look at some different type of modification. Then yeah, we are done with thermo. Alright. Probably next week only can be done. I'm not sure Thursday 1 hour can finish or not. Okay, so